Hello, students. Welcome to the Open Channel Flow class. Today, we discuss on the applications of specific energy, the concepts of specific energy and critical depth are very important in the analysis of the open channel flow problems. So we start with that applications. Mainly, there are two applications. Number one is a channel with a raised floor. A channel with a raised floor. That raised floor is called hump. The raised floor is called as hump. That means a channel with a hump. That is first. The second one is a channel with width reduction. A channel with reduction in width. These channels with hump or channel with width reduction, these two are called channel transitions. So what are channel transitions? A channel with a hump is a channel transition. A channel with a width reduction is also a channel transition. A channel with both width reduction and hump is also called as channel transition. So that means we are studying about the channel transitions because the channel transitions are the practical applications in water resources. Whenever we are constructing canals where we raised the floor at some points with a specific purpose of creating critical flow conditions. Similarly, we reduce the channel width in open channels to create conditions of critical flow. So that is why how to analyze such a flow, how to analyze a channel transition, that we discuss in this today's class. It is more a problems rather than theory, but I just introduce you to theory in today's class so that in the next class we will do two problems on hump and two problems on width reduction. So that completes the total channel transitions. So channel transitions. Two types of channel transition. Number one, a channel with a hump. A hump is nothing but raised floor. Number two, a channel with width reduction. This is generally we study to analyze the problems connected to open channel flow. And what concepts we use? We use the concepts of number one, specific energy, And number two, critical depth. These are the two concepts we will use, specific energy and critical depth, to solve any problem related to these two. So let us first start with a, a channel with a hump. For example, just understand. So this is the channel. The floor is raised like this. So this is called hump. And actually, this height is some delta z. Right? Now, to analyze this, first I assume that the incoming flow is subcritical. This is the most general case I am doing. You can assume the incoming flow supercritical also, but that is not practically which we really encounter. Most of the cases we encounter this. That is why I have taken first this. And you all know basically, if I do basic this here, if this is the case, how what will happen? You know already the specific energy curve already which we have studied, wherein on x-axis this is specific energy E, and on y-axis the depth of flow y. This is what we will plot. When we plot that, you know how the specific energy curve looks like. The specific energy curve looks like this. This is how it looks like. So it continues, right? And where this minimum energy is there, this is the minimum. Corresponding to this minimum, whatever is there, this depth of flow is called critical depth, YC, and this is E minimum, right? Now, our problem. So, if I take it from here, you know this region is subcritical and this region is supercritical. Both are separated by critical flow. Now, the incoming flow I mentioned basically subcritical. That means the depth will be in this range. Let us assume that this is the depth of flow. Initially, I call it as some P. So at P, the depth of flow is Y1 corresponding to, right? And corresponding to this, the specific energy is E1, right? Now, there is no loss of energy from the beginning onto the hump. But what will happen? So, how, but what will happen as because of this hump actually, so that means if I take it the specific energy, generally you take it what is specific energy at initial section, it is section 1, it is section 2 you take. At section 1 we call it as E1 specific energy, at section 2 E2. But when there is no loss of energy, that means the energy remains as constant. So then naturally, if this is equal to E1, total is equal to E1. This is total energy line. And here, naturally, what is E2 is equal to, if I take it, E2 is equal to E1 minus delta Z, because E1 and E2 both, if I take it, this is E2, right? So what is E2? E1 minus delta Z. So first thing is E1 is equal to E2, sorry, E2 is equal to E1 minus delta Z, as there is no loss of energy between section 1 and section 2, right? So that means the E2 is less than E1. When E2 is less than E1, what happens to the depth of flow from here? That is what I am interested. When E2 is less than E1, so that means because of this, the depth of flow there drops. So how the depth of flow will be? When it comes onto the hump, this is how the depth of flow. So at the section 1, this is depth of flow is Y1, right? Whereas here this y2 is less than y1. So that is why here if I take it, if I take it as q, so this is basically related to y2. And now if I take it, this is e2. What is the difference between these two? Is nothing but delta z. So this is the first point you should understand. Once again, when there is no loss of energy between section 1 and section 2, naturally, in the case of subcritical flow, the water surface drops. Why? Because if you take what is E1 and what is E2, the E2 at section 2 is E1 minus delta Z, which I have represented in the figure also, and you can see also how the depth decreases. So that is what I have shown here. First, this is the first thing that you should remember. That means, for example, if you are if you are raising the, if you you are raising the height of the hump, the height of the hump, right? That means this delta Z is increased to delta Z maximum. I'm increasing it. What will happen to the flow? That is the next question. If suppose when I am increasing the hump height, that means if you are raising the hump height, what will happen again? If that means delta Z is increasing, when delta Z is increasing, what happens to Y2? Y2 will be still decreasing. To what extent it decreases? It goes on decreasing from here, Y1 to Y2 it has come. Now, if suppose you increase delta Z, naturally this goes down like this. It goes down. Up to what level it can go? The E becomes E minimum at some point. When E becomes E minimum, naturally the flow becomes what? It becomes critical flow. That means the depth at the hump becomes actually, what the depth at the hump becomes critical depth. That is the second point which we should remember. So first, next one is what for us, right? So when we are talking about, so what I mentioned again, if this is the channel bottom, right? If it is your channel hump, which is delta Z, initially subcritical flow means I mentioned it as the water surface goes down. This is how it happens, right? So this is the initial depth y1, and this is what you call it as section 1, where energy is same. Energy at every point is same. Suppose now I take section 2 here. If it is E2, E2 is equal to E1 minus delta Z. That is the first thing. Then naturally, this is Y2. Right? Now, what I am telling is, if suppose increase the height of the hump, if you increase the height of the hump, the depth at section 2 decreases. That means Y2 decreases, right? And E2 becomes, E2 also reduces. If you go on doing like that, you reach a point actually wherein your hump size is equal to delta Z maximum. This is the maximum thing. So if you do that, then what is the flow condition? This is how the flow condition. So still at section 1, the depth of flow is Y1. At section 2, this becomes critical depth. And here, if you take it at section 2, E2 is equal to EC. That is critical thing. This is also called as E minimum, but energy remains as same at both the places. Suppose if this is V1 squared by 2G, this is V2 squared by 2G. So that means Y2 becomes YC if delta Z becomes delta Z maximum. This is the condition. So generally in the hump, in the case of raised floor, our objective is to create critical flow conditions. So normally in any problem, they will ask, what is the maximum height of the hump? The maximum height of the hump is such that the flow at that height hump is a critical flow. This is the point I want to emphasize. So that means again, if you remember, E2 is it becomes E minimum, that is nothing but EC, which is equal to E1 minus delta Z maximum. You know it actually. What is E1? E1 is equal to Y1 plus V1 squared by 2G. This is the specific energy definition. So if these two equations are known to us, and see next one is E2 is equal to E1 minus delta Z. These are the things that which you should know it. But out of curiosity, you may have a doubt that, sir, okay, now I increase this delta Z maximum still further. For example, suppose now I am telling you, so this is the floor. So, right, this is the hump. So it is its height is greater than, it is greater than delta Z maximum, right? If it is greater than, so already the depth at delta Z maximum, the depth has come to critical depth, right? If suppose you increase it beyond that also, if you increase beyond that, then what will happen is the upstream flow condition changes. Upstream flow conditions changes if the hump height increases beyond delta Z maximum. So kindly remember it. That means Initially, whichever we are thinking, suppose this is the original thought process. That means this is y1, this is yc at section 2. Now, what will happen if you are increasing it? This will increase. You understand? But here it will not change. This here, that the depth will increase. Y1 will increase, but Y2 will be is equal to YC only. The depth cannot go down below YC. Here the depth remains as constant. Only thing is the upstream depth conditions changes. So if you want to increase, so initial condition is some delta Z is some minimum value. At that state, what is the condition? E2 is equal to E1 minus delta Z, and Y1 at initial depth at the first section, and Y2 at the second section. This is the first condition. If delta Z becomes delta Z maximum, then naturally the E2 becomes critical flow section. The y1 remains the same, but y2 actually reduces to yc, right? This is the next. And when y2 reduces yc, automatically discharge becomes maximum. And when discharge becomes maximum, the specific energy is minimum. These are the things that you should know. Now, without if delta Z is increased beyond delta Z maximum, then basically E2 remains as critical flow section. But Y1 increases. Y2 is always equal to YC, right? Y2 cannot go down below YC, right? Because if the incoming flow is subcritical, the depth of flow can reduce from Y1 to YC. This is the minimum depth. So these are the conditions you should know. If suppose, that's what I'm telling. Suppose the same case is supercritical flow. If the coming flow is supercritical flow, exactly the same thing, but opposite in direction. Opposite in direction. So now with this, I will stop here. You can understand more when we are doing the basically problems. What is the other channel transition? Other channel transition is width reduction. All what for we will do it is we create conducive conditions to create the critical flow. Why to create critical flow? By creating the critical flow, the discharge will be maximum, and it is a section where discharge can be has to be measured easily. So now if I take that actually, so now let us take it how that also will work. So how that will work if I take it? Suppose this is a channel. Original channel is this, right? Now slowly it reduces like this. So let us assume like this. Whatever I am showing is in plan. The width of the channel is reduced, right? This is the thing. So initially the channel width is B1. Here this is B2. So this is section 1 for us. This is section 2, right? If that is the case, basically, so we know E1 is equal to Y1 plus V1 squared by 2G. It is equal to Y1 basically plus V1 is equal to what? It is a Q square by, right? Q square by basically v, v is equal to Q is equal to area into velocity. So velocity is equal to discharge by area. Area means what actually for a rectangular section, if I, because this is the rectangular section. So it is a B1 square, Y1 square into 2G. So it is Y1 plus q square by 2g into b1 square y1 square. Again, remember that channel transition we are doing only for rectangular sections, not the other trapezoidal sections. Only in rectangular sections we use the hump or making it as the width reduction. So this is one of the first equations, right? Now, if I go to section 2, for example, what is section 2? It is y2 plus v2 squared by 2g. So that means y2 plus q squared by b2 square y2 square into 2g. So this is the second. So this is one equation. This is second equation actually. So now fundamentally what is the thing? E1 is equal to at both the sections the energy remains same. Now what happens? What we will do? For example, the incoming flow is subcritical because I have to assume something and start. Then how the depth of flow will be? That why I assumed this, how the depth of flow will be. Now you know when the moment I say incoming flow is subcritical, you must get in mind actually how the specific energy curve looks like. The specific energy curve is nothing but an x-axis, it is specific energy, and y-axis depth. And if I draw that, this is how the specific energy curve. Now, what will happen actually if you observe it in this? This is for a particular discharge. Here, actually, Q is equal to basically constant. Now, what I told, width is reduced. Width is reduced. Now, this Q by Q square by B1 square. This is called as small q square, q1 square. And similarly, q square by b2 square is small q2 square. This q1 or q2 are called as discharge intensity, right? So if I both the sections, both the sections 1 and 2, the specific energy E is constant. But what is varying? because of width reduction is discharge intensity. What is discharge intensity means? Discharge per unit width. Now if you see at section 1, Q1 is equal to Q by B1. At section 2, if I take it, Q2 is equal to Q by B2. We know actually B2 is less than B1. When B2 is less than B1, what will be happening to Q2 actually? Q2 should be greater than Q1. When Q2 is greater than Q1, that means at the second section, the discharge per unit width is more than Q1. Then what happens to depth? Depth decreases. So what will happen if suppose you take this is our channel transition. So this is section 1, this is section 2, right? This is here it is B1, here it is B2. Now if I see how the water level, if I take it, how it will appear initially, it will be like this. So that means at section 1, it is Y1. At section 2, it will be Y2. Y2 is less than Y1 as Q2 is greater than Q1. This is how it looks. Now, what we will do practically in the problems is this B2 is reduced to minimum. That is B minimum. When B2 is reduced to B minimum, then what will happen? The Y2 is reduced to minimum depth, which is equal to YC. How it will happen? For example, if I write, suppose again this is the channel, this is B1. Now this you have reduced to B2 minimum. Then in such a case, what happens to the depth actually? Initially, this is how it reduces. So this is Y1. Y1 remains same, but here the depth becomes YC. So this is the condition. So we reduce what is the minimum width? Minimum width we provide by reducing channel width is is when the flow at becomes critical flow, when Y2 becomes YC, Y1 remains constant, means constant. So now we have created by reducing to minimum width, critical flow conditions are created, you can ask me, why sir all these critical flow conditions? Because it is very, very easy to analyze flow at critical section. Why? The reason being, at critical flow, equations are well defined. So that is why our preference is to get the critical flow. Suppose, like in the hump, which you have increased the height of the hump beyond delta Z maximum. Now, if you also think that if you reduce the width beyond P minimum at section 2, depth of flow is still YC only, but upstream depth increases. So in both the cases, whether it is a hump or whether it is a channel reduction, any of these cases, both the cases, only we can have this is delta Z maximum, this is B minimum. Under these two circumstances, this depth remains Y1 only, but this becomes YC. This here, if I draw the here depth remains thing only, this is Y1 only, this becomes YC. So this is generally the conditions. If delta Z is greater than delta Z maximum, Y1 has to increase. And if P reduces, B is less than B minimum, again Y1 increases, but Y2 remains YC. Y2 remains YC. This you should remember. So if anybody tries like this condition or this condition, these conditions are called choking conditions. These conditions are called choking conditions. If you create these conditions, automatically the flow gets choked. So we don't try these type of cases. So why we studied channel transition is only to create, basically the main thing is create conditions for critical flow. Why to create conditions critical flow? Because easy to analyze. Why easy to analyze? Equations are well defined. That is why we do it. And at critical flow, what are your advantages? Number one, discharge becomes discharge per unit width maximum, right? Then Y becomes YC, right? E becomes E minimum. So these are the things you should remember. So these conditions can be applied for solving any problem in with the channel transitions. So now you understand better if you do more and more problems here, because that is the real application of this particular channel transition rather than theory. So I stop this lecture at this stage, and we go for actually in the next class. We go in the next class.
Like, share, and subscribe. Hit the bell icon for more updates.